afternoon, I will talk about the ML-adjoint, then the adjoint source directly for waveform inversion using machine learning today. My name is Bingbing Sun, and this is a joint work with Tariq Khalifa, and both of us coming from King Abdullah University of Science Technology. As we know, cycle skipping is a critical issue in waveform inversions. Here we show a machine model which is inverted with L2 norm and with advanced cycle skipping free misfunctions. We can see that cycle skipping is a critical issue as long as the initial model is not accurate enough or we do not have actual low frequencies. It will create problems and create artifact geological models that is not reasonable for interpretations. So the conventional solution is that we want to get a highly accurate initial model, or we would want to acquire very low frequencies, for example, below 1 Hz. But these conventional solutions has limitations in some aspect. For example, the initial model is rather difficult to build based on the current industry standard is mostly based on ray tomography. Some complex regions like salt body is very difficult to have a very accurate initial model. Also, to obtain very low frequencies is very costly. Also, there are some old seismic data. Their low frequencies considered to be relatively high. So our solution can be considered a cost-effective solution is that we want to design more robust misfunctions. For example, now people developed more advanced misfunctions using like matching filter or optimal transport. The matching filter misfunctions, unlike conventional misfunctions like L2 norm, to which is only a local pixel by pixel comparison. The matching filter will compute a matching filter first by deconvolution of the predict data and measure data, and then using a penalty or using a normalized penalty as in adaptive waveform inversion, it can formulate a misfunction which, as the deconvolution step involved, it will have a global comparison between the predict and the measured data. Another approach of the current state-that misfunctions is optimal transport-based misfunctions. It will at first transform the predict and the measured data to be a probability distributions to satisfy the positive requirement for using the optimal transport. Then it will use a more robust and convex wavelength distance to measure their distance. Recently, we also developed a method which combines the matching filter and optimal transport. So we will compute the matching filter first, but then not using a penalty, we will using wavelength distance to measure the distance between the matching filter and its target, the Dirac data function. Our method is a unified framework for design misfunction. AWI can be considered a special case of our method. Our method can mitigate the difficulty of preconditioning the seismic data to be a probability distribution, as the resulting matching filter can be considered a probability distribution naturally. We have just discussed this state-of-the-art misfunction developed by human. So as we know now, the AI is a superpower. It achieves a remarkable success that people cannot believe before. Thus, we would like to ask a question: if AI is so powerful, why not let the machine to learn a robust misfunction for FWI or the adjoint source directly? So actually, in this year's EAG meeting, which has unfortunately been delayed, we have proposed using machine learning to learn a misfunction for FWI. So our misfunction can be formulated as a neural network. Its input is the predict and measure the data, and then output the scalar value. So to use it, we need to compute the adjoint source First, it's the derivative of the misfunction with respect to the predict data. To training the ML misfit, we use the method called mental learning. So the mental learning is a semi-supervised learning method. It can be considered a learn-to-learn method. It will learn prior knowledge for improve the solves the problem in hand. Here we show the flow for training using ML misfit using mental learning. So in FWI problem, we will have an initial model, then based the physical model, we will mold in the predict data. Then our ML misfit will measure the discrepancy between the predict data and the measured data. Producing a joint source, we can update the current models. So we need to notice that the ML misfit has related the parameters of the neural network and the adjoint source. So the updated models also depends on the parameters of the neural network. To evaluate the performance of current ML misfit, we design another loss, which is considered to be the mental loss. Then we by backpropagate this residues along the trajectory of the gradient, we can update the parameter of the ML misfit. So here the red lines we show the residue how to flow and update the parameter of the ML misfit. Before we have seen that in the ML misfit, in order to update the model, as we formulate the neural network as a misfit, we must compute a joint source first, then using reverse time migration to get model perturbation. So our motivation is that actually the misfunction is less important than the adjoint source. So this intermediate gradient computation step, the derivative of the misfunction with respect to the predict date can be animated if we mapping the predict date and measure the data to the adjoint source directly. So this will improve the stability and efficiency for training. For example, if we think our neural network is a 3 layers, the derivative of the neural network with respect to the input, which can be considered as a joint source, would be in such complex forms. If we want to update the neural network parameters, for example, W1, the actual order and a more higher order derivative should be evaluated, and this would cause instability problems in deep learning. For example, you use residual network, which can be considered relative deep neural network. The gradient exploiting and gradient validation problem would occur frequently for this very complex network. So our ML-adjoint would directly compute the adjoint source, animate the intermediate derivative step, would highly simplify the updating procedure and make it more stable and efficient. So we are the first to discuss the neural network architecture for the ML-adjoint. So in the ML misfit, our neural network architecture is defined as the L2 norm difference between the nonlinear mapping of the predict date and the measured date. So its adjoint source can be calculated naturally in these forms. So the first term is the derivative of this nonlinear transformation with respect to the predict date P. The another term is the date residue. So in our ML adjoint, we want to mimic these forms. So rather we compute the derivative of the neural network of phi with respect to P, we're using a neural network phi 1 to directly mimic this Jacobi. So our ML adjoint would be a neural network with input P and D multiplied with another neural network difference. So we can see by this formula, if P equals D, delta P will be zero directly. So this neural network architecture also makes the training process easy. For example, the neural network needed to learn the output should be zero when the predict and measure data already the same. The training the ML-adjoint is the same as the ML-misfit. The difference is that now our neural network would output a joint source directly. That means we're giving predicted P and measured data D, it outputs a joint source data P. So let's repeat the training process so you can be more familiar with the mental learning. So we're given a initial model, then we compute the predict data P, and using the measure data D, our adjoint source would output ML-adjoint would output adjoint source data P. Then note the data P is depends on the neural network parameter theta. Then we backpropagate this data P using reverse time migration to get model update. So as the data P depends on the parameter theta, so the resulting updated model M theta is also depends on the parameter of the neural network theta. So to update the neural network, we use a mental loss, which will measure the performance of current ML-adjoint. So we defined it to be the L2 norm difference between the inverted model and the true model. Then we can backpropagate this residue to adjoint to update the ML-adjoint. After introduce the neural network architecture and the training of user mental learning, now we first example present a first toy example using a time shift signals. The forward modeling problems is that we're giving a record riblet and then they shift it to produce our data. So for example here we can consider the black curves as our measured data in FWI, and the blue curve is the predict data in our FWI. So our inversion would be inverted for a travel time shift tau to reduce their distance to let the predicted P match the measured data D here. And our gradient for updating the travel time shift would be in this form. So the first term is the derivative of the modeling with respect to your model parameters. So the second term, so it's the adjoint source, which would output by the ML-adjoint directly. So it would not need to compute from the misfit by computing the derivative. So this adjoint source would output by the ML-adjoint directly now. So here we show the examples, the training examples for the training. So in order to train, we need to prepare the data. So we randomly generate a travel time shift between 0.4 and 2.1 seconds. And the mean frequency for the recurrent loop also random generate from 3 to 10 Hertz. So the figure 1 shows the average of the training nodes and the testing nodes. We can see the training curve shows continually decreasing, and the residue is very small after training. The figure 2 we show selected the inverted travel time shift from the testing results. The black curves is initial travel time. The red curves is true travel time. The dotted blue is the inverted travel time. You can see the sum at some samples, the travel time difference is very large. It's far beyond the half cycle of the mean frequency. So we can see that our ML-adjoint can successfully invert for this travel time shift with high accuracy. To further check the accuracy of our ML-adjoint methods. We plot the derivative regarding to the travel time shift, which is the gradient for updating. Uh, here, we show the x-axis is the travel time difference between the true and the predicted data, and then the curves shows the gradient with respect to the travel time shift. So we can see for L2 norm, as we know, it shows cycle skipping. It shows incorrect gradient information beyond the half cycle, while the ML misfit can show the correct sign and also scale properly with respect to the travel time shift. Also, these accuracies can maintain for across the frequencies. Now we want to apply our method to more realistic models, like the Mamushi model shows here. Here is the true models, and here is the common shift carriers modeled from the true models. We can see the data become more complex now. It's not just a single time shift event as the toy examples. We want to check our ML-adjoint can work for these complex realistic models or not. The first step, we need the prepared data for training. So we will train ML-adjoint on layered models. So because for FWI invoking for layered models, we can just invoke for one source. So that makes the training more efficient. So we will random generate layered models. This kind of layered models, the velocity is setting to be in a range similar to the Mamushi models. Here, the black curves is our randomly generated layered models. We also using highly smooth initial models. We can see this blue line shows the initial models is highly smooth. Also, in the training, our offset range is set to be similar to the Mamushi models. We can see the training rules for the test and training tasks are also drops continuously, indicating the convergence of our training. We show the layer model emerging result before training. We can see the ML-adjoint without training, it gives poorly inverted results. Here is the results after training. We can see it improves significantly. For example, these models and these models and these models, it recovered relatively good, especially at the shallow part. Of course, the results cannot consider to be perfect over all of the models because the training is we have evaluated numerous lots of randomly generated models. So the goodness is actually measured by an average sense of all these training models. Then we apply the trained ML-adjoint to the Mamushi models. We can see that ML-adjoint give relative better recovery of the left low velocity paths, while the L2 norm showed obviously cycle skipping features. So this, as the Mamushi models is relative complex of the data complexity seems has been successfully addressed by our ML-adjoint methods. It can produce a joint source without cycle skipping to properly update the models. Here is we have our conclusions. In our work, the joint source is represented as a neural network. Mental learning was suggested to train the neural network. We use special network architecture for the ML-adjoint, which mimics the joint source of the ML misfit. So our ML-adjoint would exactly improve the efficiency and stability for training. Also, this research is still in early stage. Deeper network, more advanced network architecture are still under investigation. And thank you.